Are you interested in power electronics cooling? Do you want to know how Simscape can help you design and optimize the cooling system for a high-power inverter? In this video, you will learn how to use modeling and simulation to find the most efficient heatsink for your liquid-cooled inverter. First, we will import device parameters from datasheets into a Simscape electrical model. Then, we will use detail and reduce order models iteratively to find the thermal steady state faster for different pump flow rates and heatsink choices. Finally, we will compute the efficiency, coolant temperature, and lifetime cost for different heatsink sizes. Let's get started. Let's have a look at the model. We have a three-phase inverter driving a 30 kW load. The inverter converts the DC power from the high-voltage battery into three-phase AC power. Conduction losses, switching losses, and reverse recovery losses from the IGBTs and body diodes generate heat in the case. The case contains a heat exchanger. Liquid coolant flows through the heat exchanger thanks to an electric pump system, absorbing the heat. Then, the coolant flows through a radiator, also called heatsink. The heatsink fins dissipate the heat to the environment. A fan blows air into the radiator to increase dissipation. To import datasheet parameters for the IGBTs and body diodes in the detailed inverter model, use the Import Device Parameters function. For more information, visit the function documentation page. Here are some plots of the IGBTs and diode characteristics and switching losses at different currents and temperatures. Now we have a digital twin of our inverter ready to use for electrical and thermal simulations. The inverter model contains two variants, detailed and reduced. You can use the detailed inverter variant to simulate the switching dynamics at high frequency. The detailed inverter variant consists of 6 IGBT switching devices and the corresponding body diodes. You can use the getPowerLoss function to generate a table with the conduction and switching losses for the devices. You can also use the getEfficiency function to compute the system efficiency. While the electrical dynamics are in the order of milliseconds due to the kilohertz switching, the thermal dynamics are in the order of minutes. If you're only interested in heat and temperature, you can simulate faster by using the reduced order model variant to simulate the thermal dynamics without explicitly modeling the switching electrical dynamics. You should set the simulation stop time to 1 hour to observe the thermal steady state. It is computationally intensive for a detailed model to simulate these long-term studies. You can use the detailed and reduced order models iteratively to find the thermal steady state faster. The iteration looks like this. Run the detailed model to compute the accurate losses on 4 AC cycles at a certain initial temperature, setting stop time to 4/60ths of a second. Then, run the reduced model with these losses to find the steady state temperatures. Finally, rerun this process with the new temperatures. After 3 or 4 iterations, the temperatures converge to the accurate steady state values. You can repeat this process for multiple heatsink sizes to find the optimal heatsink that maximizes the inverter efficiency and minimizes cost. In this case, the inverter efficiency increases with larger and larger heatsinks as the coolant temperature decreases, but with diminishing returns, as the efficiency increases do not compensate for the larger heatsink cost eventually. For this inverter, it seems that a heatsink of around 120 fins combines a good blend of efficiency and lifetime cost. Here's a visualization of how that heatsink would look like. I hope this was helpful. To summarize, we imported device parameters, ran detailed and reduced order models to find steady state temperatures, and computed the optimal size of the radiator for our high-power three-phase inverter. To learn more, please check the MATLAB and Simscape documentation. Thanks for watching!